Good evening, everyone. The title of my talk is a reference to the work by Jean Baudrillard, The Orders of Simulacra. And hopefully by the end of my talk, the context of this reference will become clear. But let me begin by quoting from Tamil Sanskrit literature. I happen to come from India, so it makes sense, I suppose, for me to quote from my native literature about a concept that is known as mepad, which literally translates to truth must be experiential for it to be true. And I do not expect everyone to buy into this, but if you do believe that there is some wisdom behind this notion, then perhaps this makes a very strong case for experiential learning as well. So with that, I want to share with you a story of our Mathematics Innovation Lab at Plaksha University, which is where I teach. The university is a very new university. We have been in existence for a little over 2 years now. So this practice has gone through 2 iterations with 2 batches of our undergraduate students. So what we do as part of our mathematics undergraduate course, the first 2 semesters, is have the students, as part of their coursework, do an experiential project every semester. So a group of 7 students approached me midway through the past semester, and I had at that point of time just completed the chapter on stochastic processes and queues, so they wanted to do something on queues. So I suggested to them that they should take the next 6-7 days and explore the cyberspace as well as visit their neighborhood, industries in their neighborhood, and try to identify a few problems, few applications where queues and stochastic processes may be relevant. So they came back to me about a week later. And, when they had set out, the only boundaries that I had set for them were the following: that the application must have sufficient innovation component, it must be interdisciplinary in nature, and it must foster mathematical and computational thinking, because I did not want them to wander around to, esoteric topics. So with that, they came back to me and they said, well, there are 2 applications that we have identified, one being a printed circuit board production line, and the second one being a baking manufacturing process. And in both applications, according to them, we could apply some notion of queues and do some analysis and make a model and so on and so forth. So with that, we were able to anchor the project objectives. There were 2 objectives that we identified at that point of time. The first objective was to come up with a digital reconstruction of the production line. And the second objective was to come up with an automated scheme, a mechanism, an optimization mechanism that we would be able to provide to the factory engineer, the floor engineer, which would help that person do resource allocation in an intelligent way. So that somehow related to process or engineering design. So with that, I asked them that before we actually begin doing this, we should sketch out the production line for each of the applications. So a couple of students actually sketched this out for the printed circuit board manufacturing process. What you see on the screen is what was sketched by them. As you see, this is a linear production line. The raw materials come in from the left hand side. They go through different stages of production, cutting, drilling, masking, so on and so forth, and finally the finished product is packaged and set out for delivery. But it doesn't have to be linear in the sense that is shown in on this slide. It actually is a slightly more complicated process because at every stage you could have multiple equipments and multiple production units working concurrently. So it's more like a linear mesh flow, if you like. Likewise, for the cookie or baking manufacturing process, they prepared the schemata as well. So as you can perhaps at this point, looking at these cartoons, guess that this is complex in nature because of the uncertainties that are involved at every stage of production. So there is a scope for modeling that stochastic aspect of this system in these projects. So it's not entirely deterministic, right? So that's what makes it exciting and interesting, I suppose. So we began by first preparing an abstract simulation of the process flow. And when I say abstract, I do not mean in the purest sense of abstraction or the Platonic abstraction where we're talking about ideal forms or formulae, derivation, proofs, and so on and so forth. It is the next layer of abstraction where the students developed something like an agent-based simulation of the production line, which is what you see on the screen, the side view and the top view. It is abstract because it is still far removed from the real scenario, right? It still doesn't look anywhere close to what the PCB production line and the cookie manufacturing process would look like. But it gives you an understanding of how a process flow may be simulated. So you have an array of, if you understand the lingo of queuing theory, we have an array of MMC queues where each stage comprises a bunch of queues that are feeding into the servers. You could have more than one server at every stage. The servers are represented here either in green or blue, depending on whether they are idle or they are serving a particular task, and followed by a waiting or a storage unit, right? So the process flows through the queues, the servers, and storage and moves on. So it's an array, a cascade of multiple MM queues. So the students actually simulated the Poisson rivals and the exponential service times and so on and so forth. So this is still in some sense abstraction again because we have representations. For example, the cylindrical looking thing represents the server, the white markers represent the queues, the orange pathway represents the queue for the defective part, so on and so forth. So it's at this point of time still a representation, a mental imagery to follow what's happening in the production line. Once we did that, we wanted to identify the elementary units of this abstract model. So the elementary unit of this abstract model is a simple queue and a server, right? You see on the left hand side, the tasks come in and join the queues, and then the task at the head of the queue goes into service, which is served by the server for a random period of time, after which the task moves on to the next stage. However, it looks nowhere close to the real situation. Like I mentioned, something more realistic would be what you see on the right hand side, which is a reconstruction of an elementary unit of this production line, where the sheets come in a queue. The worker picks up the sheet, feeds it to the machine. It's a mechanized component placer which places the components in a designated manner, the electronic components on the sheet, and then after all the components are placed, the worker picks up the piece and then passes it to the next stage. Now, it's more or less simple so far, but the challenge at this point was to integrate all these assets, digital assets, together as part of the full production line, right? So, which is what the students, had to do next. Now, before I play the simulation or the digital reconstruction of the production line, I must say there were many challenges. One of the biggest challenges was, this is being currently hosted on a website server. So memory is an issue, right? We don't have access to a lot of memory, which means that when we created these digital assets, the students had to keep the poly count of each asset very low, so that we don't get Stack Overflow. So you will see that this will give you a boxy look in the scene. In the next iteration of the project that we hope to continue in the subsequent semesters, the students will actually do this and incorporate this in a local server where memory will not be such a big problem. But that has its own challenges, and we'll deal with that when we get there. So anyway, you'll see boxy type look when I play the simulation. The other thing is, it kind of gives you a Super Mario feel. But I, honestly speaking, do not mind. I wish when I went to university, we made Super Mario and played Super Mario stuff in classrooms. Life would be far more exciting, wouldn't it? So anyways, like I, mentioned at the start of my talk, this is different layers and iterations that the digital reconstruction will, go through. And eventually, the idea is that after multiple iterations, we will get to a point where the simulation will look very realistic. In fact, I'll come back to this actually. Let me mention the second project objective here. So you see the digital reconstruction was done by the students. The next thing that we wanted to do is to provide a mechanism, an interactive framework for the factory engineer, the production line engineer, to interact with the avatar. The avatar was actually constructed by the students, and actually feed in certain requirements, profile requirements, what my response time, for example, in this complex process should look like. So the factory manager would put in some parameters, and the avatar, would collect all these input parameters through a conversation and then feed it to machine intelligence. And when I say machine intelligence here, I'm talking about a family of algorithms that the students developed under my supervision. Things like Bayesian methods, statistical learning methods, optimization algorithms like mixed integer programming, Erlang C formula implementation through for a MMCQ, so on and so forth. So I think there are 4 algorithms right now which are integrated with this model. So one of these algorithms, or one or more of these algorithms, will kick in depending on the query being raised by the factory manager, and some output will be generated, which is in technical language. And then the students actually learn to use ChatGPT APIs to massage that output, that technical output, in a more understandable language. And the avatar would read it out, and it would get displayed at the same time. So let's watch for a little while to see if what I said makes sense.
Please enter the mean value.
At this time, actually, I should also mention that there is speech to text and text to speech conversion going on in this framework, which actually is a setup that has been developed by our industry partner. The students did not do that, but they learned how to use the speech to text and text to speech converters. So anyways,
please enter the standard deviation.
As you can see, the manager types in all these parameters. In this particular case, it's the mean response time profile and the tolerance parameter that he or she feeds in, which is then collected by the avatar and fed to the to the machine intelligence. And you will see something pop up, and the avatar will speak it out. There you go.
The algorithm used is a maximum a posteriori estimator that works on a Bayesian statistical model. This estimator determines the most probable outcome. According to the algorithm's findings, the most likely configuration for the given input profile is U11170.
So U11170 is, in some technical language, it corresponds to a particular configuration where, the number of servers are being specified at every stage. That's what it means. So here's another set of conversation which has been initiated. So I want to minimize the cost of my operation.
Please enter the Q cost values.
So the avatar asks the factory engineer to enter the per unit cost of operating the queues.
Please enter the server cost values.
Now the avatar asks for input for this operating cost of each server. So the manager types that in. There are 7 levels in this particular case, so he or she has to plug in the numbers for each of the levels. And then submits the query. And here you go. The algorithm spits out. This is already massaged.
The algorithm has optimally run a mixed integer programming for constrained optimization. It sought out a configuration with the least operating cost. The optimal configuration found by the algorithm is 1, 0, 1.0, 7.0, 1, 0.
So you get an idea of the kind of interaction and conversation that is actually happening in real time. I must say that we are still working on the accuracy. Actually, to be honest, in the case of 2 levels, multiple servers, for example, 4 servers, we go from an accuracy of 100% for the Bayesian method to an accuracy of 0% when we have 4 levels and more than 2 servers per level, right? So this has probably, my hunch is, something to do with the distribution of the prior probabilities in this particular case, and that has to be sorted out. So anyways, we were not too concerned with the accuracy part. We wanted to get the implementation going, and one of our next tasks would be to work on the accuracy and actually understand how the algorithms work under different input parameters. So anyways, hopefully that gave you a sense of how this game, if I can call that, was developed by the student. This was done from scratch, I must say. During the semester, we got about an hour and a half per week of training that the students had to undergo, and that training was conducted by my industry collaborators, Dave AI. And after that, we would meet every other day online, because all of us were in different places. People from the industry were in Bangalore, some students were at home, some students at Plaksha campus. I was myself traveling to US during the summer, and a couple of students were outside India as well. So but we worked very collaboratively, I must say. Towards during the summer, the contribution was full time from the students, and we would come in every now and then, roughly 2 to 3 hours per week, to help them troubleshoot whenever they were stuck with anything, and to give the broad overarching outline and strategy for pursuing the particular project. But they did a tremendous job, I would say. And, there are 2 postulates at this point of time that I am pretty confident of, making here. These are claims that I'm making. The first one is that learning is not a linear process. It is a hodgepodge of things. It is a self-assembly, a self-organization of complex ideas put together. Not all of it would make sense to a student at the beginning, right? Some things make sense, some things make more sense than other, and it's all right for it to be unstructured and chaotic in that process, if that process is that way. And yet you see that the students are able to accomplish a fairly complex project where they required, as is being shown on the slide here, they had to understand several mathematical concepts, some of which they were lectured and taught in the class, some of which they had to discuss with me and clarify further. They had to obtain and acquire a whole suite of tech applications like Blender, Unity. These are not very simple stuff, and they had to learn coding, C#, Python, and actually use that in different contexts, either in the UI UX or while coding the application, or by making integrating all that assets that they made in Blender, but they had to put all that together Unity. So this is a very complex project, and yet at the end of it, and even during the process, the students had a lot of fun doing it. I could see the enthusiasm, right? So this is important for us to understand that learning can be chaotic, it can be unstructured, and that aspect of learning must be celebrated, it must be encouraged and not discouraged. It must not be inhibited, right? Sometimes we get too hung up and stuck in very linear way of thinking. That's old school, I would say. Learning outcomes, mapping learning outcomes to assessments, and doing all kinds of exams and quizzes. This is a linear way of doing things, linear way of assessing, linear way of conducting your academic exercises. It doesn't have to be that way. I strongly believe that from the core of my heart, and it is important to appreciate that. That's my first postulate. My second postulate is a framework that I have presented here, where I have tried to deconstruct mathematics. I have tried to situate the learning and practice of mathematics between two binary opposites, abstraction and simulacra, right? For too long, education and math education has centered around abstraction, examples, proofs, theorems, derivations, formula, and that has gone on for too long, for many, many years. And what I'm pushing for is a decentering of that process, which is what deconstruction means. Decentering and swinging the momentum towards building simulations, hierarchical simulations, right? These simulations will have to undergo multiple iterations, which is what is the notion of order of simulacra. And that is very important because it opens up new dimensions of learning, right? It makes learning transcendental in nature and not inhibitive and restrictive. And the simulations have a charm of their own. And I say that because, to an extent that this digital reality, this digital reconstruction or simulation that the students have built, over a period of time will become indistinguishable from what is real, from what we observe in real life, in our surroundings, in our immediate environment, right? And which is what Jean Baudrillard talks about in his third order of simulacra. Digital twins will become our alter ego and worthy residents of an empowering metaverse, right? So that is important as well, to swing the pendulum the other way. And why is that necessary? Because then you can have a play and dance between abstraction and simulation, abstraction and simulacra, and a continuous back and forth that happens, right? So this decentering is important, because in this play and in this dance will you enable imagination to happen, intuition to be developed. And that is very important for creativity, at least as far as I am concerned, very important for innovation. These are virtues that we want our students to imbibe in them, to become 21st century engineers, 21st century problem solvers, entrepreneurs, so on and so forth. So that's, my second proposition. I will stop philosophizing at this point of time, although I think there is a strong case for us to reflect on these two propositions, and hopefully we'll have a conversation around that when we get a chance. I want to finish this talk by sharing with you guys this snapshot. You see the 7 students who worked with us They were from the first and second year, so second semester and fourth semester students. I think they did a wonderful job in whatever they accomplished, and the baseline that they set in terms of the project. On your left, you see Soham. He's from DVI, and there were other people involved from DVI, but Soham put in the maximum amount of work with the students and with me to get this done, and that's me in the middle with the Chicago landscape in the background. So with that, I want to thank all of you